Good morning, good afternoon, and good evening, everyone. Welcome to another RTDS Technologies webinar and demo. Today's topic is Power Hardware in the Loop Testing Fundamentals. My name is Katie Sidwell with RTDS Technologies, and I'll be your host and moderator today. My co-presenter is Christian Jeggs. He's our internal Power Hardware in the Loop specialist here at RTDS. Today I'm going to begin with some housekeeping notes and a brief general presentation for folks who may not have joined our webinars in the past, and then we'll get on to the main presentation. So if it's your first time using this webinar platform, please note that we are accepting questions all throughout the presentation today in the Q&A widget. So the chat window is a great place to introduce yourself and let us know where you're joining us from, but please direct your questions to the Q&A widget, and then we'll be answering those questions in real time via text throughout the program, and we'll be selecting a few of them to discuss at more length at the end of the webinar. Also, keep in mind that this webinar recording will be made available. It will be uploaded to our YouTube channel where you can view it anytime, or you can use your credentials from registering to log back in and re-enter this platform and view it this way. If you're viewing it on demand, you can still ask questions in the Q&A widget, and we'll respond to you via email. We'll also be creating a Q&A document, and that will be emailed out to all the participants along with a recording of the webinar and the presentation file. If you're looking for the presentation file right now, you can find that in the Handouts widget. You should be able to download a PDF of the slides there. And last but not least, I wanted to apologize for a couple of audio issues in this webinar. We just had some issues with changing microphones, so you might notice that even my audio quality right now is a bit lower than usual. So thank you for sticking with us, and it'll be a bit clearer next time. On with the show. Today's webinar is really designed for folks who are new to Power Hardware in the Loop testing or who want a comprehensive overview of the basic principles and to know exactly what this kind of experiment looks like with the RTDS simulator from both a hardware and a software perspective. So after I speak briefly on our technology, Christian is going to present with the fundamental PHAL theory and considerations for these types of tests. And then we'll do a demonstration where we're combining some video of the actual hardware being used with software screen share. So I hope that's helpful. And then we'll go into the live Q&A. If you're not familiar with RTDS Technologies, we're headquartered in Winnipeg, Manitoba, Canada, where there is a strong power systems and HVDC research community due to the nature of our power transmission in this region. And we pioneered real-time power system simulation back in the mid-1980s. So our product, the RTDS Simulator, was the first ever real-time power system simulator. And today it's the industry standard for real-time simulation and closed-loop testing. It's used worldwide by electrical utilities, protection and control equipment manufacturers, research and educational institutions, and consultants. You can learn more at our website. We also have a large library of videos, webinars, and tutorial videos on the RTDS Technologies YouTube channel, so check that out as well. The simulation that you see in today's demonstration is electromagnetic transient or EMT simulation. EMT simulation provides a time-varying instantaneous value output. So the simulation output ideally gives you a waveform like the one shown here, which matches the current or voltage waveform if it was to be measured from the real system. So this really differs from transient stability analysis and other tools that give you phasors as a simulation output. EMT simulation allows for a greater depth of analysis over a wide frequency range and the ability to reproduce fast transients on the power system. And the higher the sampling frequency of the simulation, the higher frequency results you can accurately reproduce. The period of the sampling frequency, or the distance between two consecutive outputs, is called the simulation time step, or delta t as shown on this slide. And the typical time step for the RTDS simulator is in the 25 to 50 microsecond range. So why choose EMT simulation? Which situations necessitate an EMT study? For steady-state analysis, phasor or RMS-based solutions do provide satisfactory results, and they've been traditionally the most widely used type of model from a power systems planning and operations perspective. And this is because it's relatively accurate for systems that are dominated by synchronous machines, like the grid traditionally has been. The issue presents itself when we migrate away from rotating machines and toward inverter-based generation and loads and their controls, like we are more and more in the modern grid. So RMS models lack the ability to capture subcycle phenomena associated with transients that might occur in a network where inverters and their control are present. And they also don't have the ability to represent those low-level controls. We've seen increasing evidence that, particularly in systems with a high penetration of converter-connected generation or loads, phasor simulation provides optimistic results, and EMT simulation might be preferable or necessary in these situations because it provides more realistic results and it's more likely to reliably predict things like control instability. The RTDS simulator executes its EMT simulations in real time. And this real-time aspect is what separates the RTDS simulator from offline or non-real-time EMT programs, such as PSCAD, for example. So when we say real-time, we mean the computer needs to solve all of the equations for the network in real-world time equal to or less than the simulation time step. This means the real time for a power system event to occur is equal to the simulated time. So a 3-cycle fault for a 60 Hz system takes 0.05 seconds, and it would take 0.05 seconds to simulate using the RTDS simulator. Offline EMT simulation programs run on standard PCs rather than using dedicated parallel processing hardware, so the time they need to complete these simulations is much greater. And that's one of the advantages to transitioning to real-time simulation, the efficiency. The main advantage, though, of running simulations in real time is the ability to connect external hardware to the simulation and test it in a closed loop. And closing that loop means not only observing the response of a protection or control device to an imposed signal, but also interfacing the external device's response back into the simulated network. This type of testing, also called hardware-in-the-loop testing, is only possible if we're updating the inputs and outputs of our simulation continuously in real time. It's not possible with an offline simulation or with open-loop testing tools like a relay test set. Hardware-in-the-loop testing also allows for the testing of multiple devices at once, more of a systems-level testing approach. And in a modern system with distributed energy resources, multiple tiers of control, our users find it valuable to be able to test interoperability and interactions between these different systems. Traditionally, hardware-in-the-loop testing has been done with protection and control equipment, but more recently, the concept of connecting power equipment like renewable energy hardware, converters, motors, and loads to the simulator in a closed loop has emerged as a popular application. And that is referred to as power hardware in the loop testing, or PHIL testing, and that's what we're discussing today. To do nodal analysis on the power system with a 25 to 50 microsecond time step is very intensive, and of course the processing power required increases with the size and complexity of the network that you want to simulate. To achieve this, the RTDS simulator is built on dedicated parallel processing hardware, specifically integrated for the real-time simulation application. Our current hardware generation is called NovaCore. You'll see it in the hardware demonstration today, and it's based on a powerful multi-core processor that we've developed at the embedded level. We achieve modularity through core licensing. So the quantity of cores licensed on a given unit determines the size and complexity of the simulation that it can run, and multiple units can be connected together to achieve larger scale simulations. In order to connect the simulation to external equipment to realize that closed loop, we use modular analog and digital input and output cards. So for example, here you see an analog output card, which might be used to send power system voltages and currents from instrument transformer models in the simulation to a physical protective relay. The interface with external equipment can also be created based on standard compliant communication, such as IEC 61850 or Modbus protocols. To do so, we use what we call the network interface card, which is also shown on this slide. We also have the capability to interface to external equipment via the Aurora Protocol. So this is a high-speed serial protocol developed by Xilinx, and it allows for the interfacing with external devices via optical fiber. So it basically eliminates the need for conventional I/O in both the PHIL application and in other applications as well. And RTDS has worked with a few different four-quadrant amplifier manufacturers to develop an Aurora interface. So the amplifier can be connected to the RTDS simulator with a fiber cable. And Christian will be demonstrating that today and talking a little bit more about it. All right, thank you for your attention through this brief introduction. I know it's likely review for a lot of you, which is why we're selective about which webinars we do include this information in. And I'm happy to pass it off to Christian for his PHIL presentation.
Hi everyone, my name is Christian Jeggs and I'm one of the application engineers at RTDS Technologies. And today I'm going to be giving you a presentation on power hardware and loop testing fundamentals. Just a brief overview of today's presentation. I'll begin by giving an overview of power hardware and loop. We'll talk about the differences between open and closed loop testing setups. I'll touch on some of the motivating factors behind power hardware and loop, some of the key factors to consider when performing power hardware and loop simulation. Also explain how our digital interface works. And then I'll present some power hardware and loop components. Finally, we'll have a demonstration where we interface a PV panel and microinverter with the RTDS by using power hardware and loop simulation. First, I'd like to touch on hardware and loop testing with the RTDS. This is going to be broken down into two main categories, one being control hardware and loop, and another being power hardware and loop. Let's first start with control hardware and loop testing. So in control hardware and loop testing, as the name suggests, what we're doing is performing a hardware and loop test on a controller. So on these slides here, you can see a hardware and loop test setup for a protection relay, which is going to act as our controller. So in this setup, the entirety of the power system is going to be modeled inside the RTDS simulator. Then, in order to interface to the controller, we need to send some signals out, like the secondary side voltages and currents, and get those signals to the device under test. We also need to bring some signals in, such as the trip and reclose commands from the relay. We need to bring those signals back into the RTDS simulator. So in this setup here, you can see that we'll be sending out the secondary side voltage and current signals from the simulated power system to our analog output card. Now, depending on the relay and whether or not the relay has a low-level interface connection, we may need to use an external amplifier to first boost these signals up to the correct voltage and current levels before we connect them to the controller. That's the purpose of this amplifier shown here. It takes the low-level electronic level voltages from the analog output card and boosts them up to the appropriate level so that they can be input into the protective relay. Then we need to bring the trip and reclose signals back from the relay and into the RTDS. This is done by using one of our digital input cards. In this case, we're going to be using the front panel interface card to bring in the dry contacts from the relay so that we can trip and close the breaker in the simulation. So some of the key points to note here in this control hardware and loop setup is that the entire power system is being modeled within the RTDS. The other point to note is that the amplifier here isn't really exchanging any significant power to the device under test. The amplifier here is really only being used to boost the voltage and current signals up to the appropriate levels so that the relay can accept these signals. Also, the output signals of the amplifier here are, relatively speaking, lower level voltages and currents. We'll see when we have a look at the power hardware and loop setup that the voltage and current requirements from the amplifier here might be significantly higher. Okay, now if we move on to looking at a power hardware and loop setup, here you can see we have a setup where we have a power device being interfaced with the RTDS simulator. Now this power device could be any high power device such as a motor or an inverter. And the idea is that we want to interface this power device with the simulator such that it behaves as if it was really connected to the power system being simulated inside the RTDS. So really what we're doing here is we have a portion of the power system being modeled and simulated inside the RTDS, and another portion of the power system, here the power device under test, which is being interfaced with that simulated power system. Now the way that we create this interface is by sending signals out of the RTDS and bringing signals into the RTDS. So here you can see we might send out a voltage command via the analog output card and feed this voltage command into an amplifier. Now this amplifier is a little bit different than the amplifier I had shown in the previous setup for the control hardware and loop setup. Now this amplifier used in the power hardware and loop setup is what is known as a four-quadrant amplifier. And these amplifiers can operate in all four quadrants of the power plane. That means that these amplifiers are capable of both sourcing and sinking active and reactive power. We need to use these four-quadrant amplifiers when performing power hardware and loop testing because the power device under test may be absorbing or supplying power at different moments throughout the test. So we need an amplifier that can both source and sink the power accordingly. Next, we need to take some feedback from the power device under test and feed that back into the RTDS. This is typically done using sensors. Oftentimes, these transducers will be embedded in the four-quadrant amplifiers themselves. Then the signals from these sensors can be brought back into the RTDS simulator by using the analog input card, as I've shown here. So let's just go over again what some of the differences are between the power hardware and loop test setup and the control hardware and loop test setup. In the power hardware and loop setup, essentially what we've done is we've split the power system into two parts. One part that's being modeled inside the RTDS, and another part that's being interfaced with the RTDS by using a four-quadrant amplifier. This four-quadrant amplifier is necessary so that we can have the proper power exchange between the power device under test and the RTDS simulator. Also, since the device that we're interfacing here is a power device, these devices will typically require higher levels of voltages and currents to be output from the amplifier compared to the previous scenario where we showed in the control hardware and loop test setup. Okay, now I'd like to touch on the difference between open loop testing and closed loop testing when it comes to power hardware and loop. Now, some applications might consider an open loop test as a power hardware and loop test, but really the challenge comes from closing the loop. So all of the further discussions that we're going to have in these slides in the demonstration today are going to refer to closed loop power hardware and loop testing. So here you can see a diagram I've shown for both the open loop configuration and the closed loop configuration. The testing tool in this diagram would be the RTDS, and the device under test would be whatever power device we plan on testing. So we can see that in the open loop configuration, the RTDS would be sending signals, say, to a four-quadrant amplifier to apply some voltages to the device under test, but there wouldn't be any feedback from the device under test brought back into the RTDS. This means that the influence is only traveling in one direction, meaning the RTDS is only able to influence the behavior of the device under test, and that since there's no feedback in the open loop configuration, the device under test isn't able to influence or impact the simulation happening in the RTDS. Now, if we compare this with the closed loop setup, we can see that in the closed loop setup, the device under test actually has a feedback path where it can impact the testing tool, here, the RTDS. So now the two systems are fully interfaced with each other, and the RTDS is able to impact the behavior of the device under test. And similarly, the device under test is able to impact the simulation results of the power system included in the RTDS. Again, the challenge of this power, hardware, and loop simulation really comes from the closed loop setup, because as soon as we close the loop, this is where we can have issues relating to the stability of the closed loop simulation and so on. So what are some of the motivating factors behind power, hardware, and loop testing? Well, oftentimes the power device that we want to test is a black box, meaning that we don't necessarily know the circuit topology or the control details of the device that we're planning to test. Because we don't know these pieces of information, it makes it very difficult to try and create a model for this device. So instead of creating a model for this device, what we do is we use power, hardware, and loop instead, and we interface this device with the RTDS simulator. Power, hardware, and loop is also very useful if you want to test increasingly complex control circuits, ones that would be very difficult to model within the RTDS. Some of the current applications for power, hardware, and loop include power converter testing, distributed and renewable energy integration, microgrids, and shipboard machine drives. Okay, so what are some of the key factors that we need to consider when performing power, hardware, and loop simulation? Well, first off, let's think intuitively about what it is that we're trying to accomplish. What we'd like to do is interface the power device under test with the power system simulated inside the RTDS in such a way that the interface is as transparent and as seamless as possible. What we mean by this is that the power device under test should have no clue that it's being interfaced to a simulated power system. So what we can do is look at each of the individual components that build up this interface and identify what impact they might have. So in this diagram here, we're showing an interface that uses an analog output, an analog input card, as well as some sensors and a four-quadrant amplifier. So each of these components that build up the interface are going to contribute some imperfections to the interface. These are things like time delays or perhaps even some noise. So all of these imperfections need to be taken into account so that we can understand how they impact the simulation results. The next thing we need to consider is the size of the simulation time step used in the RTDS. The size of the simulation time step used in the RTDS is going to dictate the frequency range over which the simulation results are valid. The size of the simulation time step will also dictate how frequently data is transmitted and received in the RTDS. Lastly, we'll also need to consider the characteristics of the four-quadrant amplifier. The characteristics of the amplifier, such as the rise time, the slew rate, are all going to be important to consider how that might impact the overall accuracy and stability of the power, hardware, and loop simulation. At this point, I'd like to point out that we have a report available on our website which documents our experiences with this power, hardware, and loop simulation, and it goes into much greater depth than what we're going to present here today. This report discusses several important topics such as interface algorithms, four-quadrant amplifiers, characterizing the interface, and the stability and accuracy of the interface. If you're interested in a more detailed overview of this material, I'd suggest you review this report. Okay, next I'd like to talk about the digital interface that we have in the RTDS. The digital interface allows us to eliminate the use of the more traditional I/O cards shown previously, such as the analog output and analog input cards. And instead, what we can do is use the Aurora communication protocol to create an interface between the RTDS and certain vendors' amplifiers. The idea is that by using a fully digital interface, we can reduce the amount of delay present in the interface, as well as eliminate any noise. The hope is that this will improve the stability and accuracy of the power, hardware, and loop simulation. So what I've shown here are the two digital interfaces that we have. In the figure above, we can see a digital interface between the RTDS and the SPS APS amplifiers from Spitzenberger and Spies. We also have a digital interface with the extant piezo system. In this interface, we require the use of a gtfpga unit between the RTDS and the extant piezo system. More about these interfaces in a moment. Now I'd like to quickly touch on some of the power hardware and loop components that we have available in our software, starting with the extant gtfpga component. Now this component embeds the digital interface and interfacing source into a single component. And what we've done is we've optimized the timing for when the data exchanges occur to try and further reduce the loop delay. We've also embedded a user-controlled feedback switch in the component so that the user can easily switch between open and closed loop operation. Now this slide here shows the hardware setup for this component. We can see that when interfacing the RTDS with an extant system, we require a gtfpga unit between the RTDS and the extant cabinet control device, or CCD. So we need one fiber optic connection from the back of the RTDS to the back of the gtfpga, and another fiber optic connection from the front of the gtfpga to the extant CCD. Next, I'd like to talk about the SPS component. This is a component that embeds the digital interface and interfacing source into a single component for use with the SPS APS amplifiers. Again, we've optimized the timing of the data exchange to try and further reduce the loop delay. Now the user has the option to select from 12 different APS amplifier models, as well as using user-defined scaling factors. Again, the component has a user-controlled feedback switch embedded so that the user can easily switch between open and closed loop operation. The RTDS and the SPS amplifier are going to communicate with each other by using the Aurora communication protocol. This slide here shows the hardware setup for this component. We can see that it simply requires a single fiber optic cable between the back of the NovaCore and the back of the SPS amplifier. This digital interface eliminates the use of the more traditional I/O cards, such as the analog output and analog input cards. It also greatly simplifies the wiring and eliminates any possibility of user error when wiring. Lastly, I'd like to talk about the power hardware and loop GTAO/GTAI component. What this component does is it combines the GTAO, GTAI, and current source component into a single power system component. And the idea is that by doing so, we can eliminate any unnecessary delays when transferring the signals from the GTAO or GTAI component between the current source. Okay, next I'd like to talk about today's demonstration. In today's demonstration, we're going to be performing a power hardware and loop simulation with the RTDS by using a PV panel and microinverter. This slide here shows a brief overview of today's demonstration. On the right-hand side, you can see the power system that's going to be simulated in the RTDS. And what we'd like to do is interface this power system with a real PV panel, which is connected to a microinverter. What we'd like to do is have the PV panel absorb some energy from the sun, and inject the power through the microinverter and into this power system here. We can see that in today's demonstration, we're going to be using a 255 watt PV panel with a 225 watt microinverter. So you'll hear more about the details of this demonstration in the sections that follow.
Okay, I'd like to start by giving a quick overview of all of the hardware that's going to be used in today's demonstration. Here you can see some video of the complete setup. And what I'd like to do here is just work through each of the individual components one by one. So if we start here on the right hand side, we can see we have my laptop PC, which is connected to the NovaCore chassis. So my laptop PC is using the RSCAD FX software. That's how we're going to build our power system model. We're going to execute that power system model on the NovaCore chassis. If we have a look at the NovaCore chassis, you can see at the back of the unit there's an orange fiber optic cable here. This orange fiber optic cable connects to this next device over here. And this device here is our four-quadrant amplifier. So this is a four-quadrant amplifier from SPS, and this is the amplifier that we're going to be using in today's power hardware and loop demonstration. So the RTDS is going to be sending commands to this amplifier, and the amplifier will be returning voltage and current measurements back to the RTDS. So all of this data exchange is done using that fiber optic cable I showed. The two devices are going to communicate with each other by using the Aurora communication protocol. Okay, so if we look at the output of the amplifier, to follow this cable here, we follow that down, and we can see that that cable connects into this multimeter here. So we're going to be using this multimeter to monitor the voltage output from the SPS amplifier. And we also have another meter here that we're going to be using to monitor the current. So we can see that there's another connection to this meter connected to the output of the amplifier. And this is the AC side of the device under test, which in today's demonstration is this PV inverter. So we have the AC side of the inverter here. This is an inverter from Enphase, connected to the output of our amplifier, while the DC side of the inverter here is fed from our solar panel. So let's have a quick look outside and check out the solar panel. So you can see the conditions today are pretty good. It's a very nice sunny day. It's about minus 15 degrees Celsius, which is about 5 degrees Fahrenheit. So outside on the patio of our office here, we have our solar panel set up on some tables. Okay, so the solar panel is going to absorb the energy from the sun. That power is going to be fed through the inverter. We're going to interface that inverter with the power system that's simulated on the NovaCore. Okay, so that concludes today's overview of the hardware. I hope you enjoy the rest of the demonstration.
I'd like to start by giving a brief overview of the draft case that's going to be used in today's demonstration. First, recall that the goal of today's demonstration is to interface a PV panel and microinverter with a power system simulated within the RTDS by using power hardware in the loop. Since the PV microinverter used in today's demonstration is a single-phase inverter, the corresponding power system modeled inside the RTDS is also a single-phase system. Let's quickly go over each of the components that make up the power system model. First, we have a single-phase voltage source here, which is used to represent the AC grid. Downstream of that, we can see that we have a user-controlled breaker, which is controlled by using this switch here. This breaker connects the load to the grid. The load is modeled as a resistive load with a variable resistance that can be controlled by using this slider here. This allows the user to vary the load and experiment with different loading conditions. Next, we can see that we also have a fault branch between the grid and the load. The controls for this fault branch are contained within this hierarchy box here. If we open the hierarchy box up, we can see the controls that allow the user to control the fault. The user has access to a slider where they can control the duration of the fault, and then the user can initiate the fault by pushing the push button. In addition to these fault controls, we also have another hierarchy box which contains several other auxiliary controls. This includes controls for things such as power meters for monitoring the power of the grid, load, and PV inverter, RMS meters for computing the RMS quantities for the voltage and the current, signal scaling, which is used for plotting purposes. And these sliders over here allow the user to control the min, max, and internal resistance values of the SPS amplifier, but more on that later. Down here we have some controls that are used for a feature known as the external plot update. The external plot update allows the user to use signals within the draft case to automatically update the plots in runtime. In this demonstration, we're going to be using the external plot update component to automatically trigger the plots to update when the PV inverter starts up. This is done by comparing the power from the PV inverter to some user-defined threshold, which is configured by using this slider here. Once the power from the PV inverter exceeds this threshold, we know that the PV inverter has started up and that it's time to use the external plot update component to automatically trigger the plots to update. This will allow us to capture the voltage, current, and power waveforms on the plots in runtime during the startup process. Lastly, we have the SPS component here. This component, combined with the use of the SPS amplifier, is how we create the interface between the simulated power system and the PV inverter. Since we are using the ideal transformer method, we need a current source on one side of the interface and a voltage source on the other. In this demonstration, the SPS amplifier has been configured to operate in the constant voltage mode of operation, which means that the amplifier effectively behaves as a voltage source. As a result, we have a current source on the simulation side of the interface. The way this interface works is whatever voltage appears across this current source, that voltage is sent to the SPS amplifier as a voltage command. The SPS amplifier then outputs this voltage, and as a result, some current will flow. Measurements of the voltage and the current are then sent back to the RTDS. Now, whether or not these voltage and current measurements are used to control the source depends on a user-controlled feedback loop switch, which is embedded inside the component. This switch allows the user to switch between open and closed loop operation. If the feedback loop switch is set to open, then there is no current injected by the current source, and the power hardware and loop setup operates in an open loop configuration. However, if the feedback loop is set to closed, then the measured current is automatically injected by the current source, and the power hardware and loop setup operates in a closed loop configuration. The data exchange between the RTDS and the SPS amplifier is achieved by using the Aurora Communication Protocol. Okay, now that we've finished with the overview of the power system model inside the RTDS, let's compile the case and have a look at the hardware requirements. Okay, here we can see that this system can be simulated with a single NovaCore chassis with one licensed core. Okay, this completes the overview of the draft case for today's demonstration.
Okay, now we've made it to the runtime environment for our demonstration. I'd like to start by just giving you a quick overview of how the runtime environment is set up. Now, the first thing you'll notice is that I've overlaid a graphic of our power system that we've modeled inside the RTDS onto the runtime canvas. On top of this graphic, I've also overlaid several other things like meters, switches, sliders, and push buttons, so that once the simulation is running, we can easily observe the voltage, current, and power flow at different points. This is the power system that's going to be simulated on the RTDS simulator by using this NovaCore chassis. This NovaCore chassis is connected to the SPS amplifier by using a fiber optic cable, and they'll communicate with each other by using the Aurora Communication Protocol. Once we simulate the power system, whatever voltage is across this current source, that voltage will be sent to the amplifier as a voltage command, and the SPS amplifier will apply that voltage to the microinverter here. The DC side of the converter is going to be fed from our PV panel. Now, whatever current flows out of the SPS amplifier, that current measurement will be sent back to the RTDS, and then we can choose whether or not we'd like to feed that current back into the simulated power system. We can do that by using this feedback loop switch here. When the switch is set to open, the current is not fed back to the current source. However, when we flip the switch and change it to closed, Then the current measurement is used to control this current source here, which closes the loop between the simulated power system and the PV inverter. Now if we scroll down a little further, we can see that I've created 3 sets of plots and 3 power meters here. These plots and power meters will allow us to observe the voltage, current, and power for the grid, load, and PV inverter. Okay, so we're just about ready to start the simulation, but before we start, I'd just like to have a look at the measurements displayed on the meter, as well as the measurements and voltage command displayed on the front display of the amplifier. Notice that all these displays are showing 0 right now, and that's because we haven't started the simulation yet. So let's go ahead and start the simulation. Once we've started the simulation, the RTDS begins simulating this power system here. You can see that we have a resistive load consuming 248 watts, and all 248 watts are being supplied by the simulated grid. You can see that the power and current coming from our PV inverter is 0. This makes sense because the feedback loop switch is currently open. Now if we look at the front display of the SPS amplifier, we can see that the voltage command is 239 volts. This makes sense because the RMS voltage across this current source is currently 239 volts. If we look at the measurements of our voltmeter, you can see that it still shows a measurement of 0, and this also makes sense because we haven't enabled the output of the SPS amplifier yet. Now before we enable the output of the SPS amplifier, so that we can apply the voltage to our microinverter, let's have a quick look at the manual for the microinverter. So this is the installation and operation manual for the end-phase microinverter. And if you have a look through this manual, you'll see that there's a note that says the microinverter will begin producing power after a 5-minute wait time. This means that once we enable the output of the SPS amplifier, we still need to wait an additional 5 minutes for the microinverter to begin producing power. There's also some other important points in the manual about the LED on the underside of the microinverter. This LED indicates the different states of the inverter, both during the startup process and during the post-startup process. If we look at the table for the startup process, we can see that a red flashing light indicates the inverter has not detected the presence of any AC voltage from the grid. However, in the post-startup process, a flashing orange light will indicate that the AC grid is normal, but there's no communication with an onboard device. Okay, the next step is to turn the output of the amplifier on. Once we enable the output, we can start our timer for a 5-minute startup time. So let's go ahead and do that now. Okay, I've turned the output of the amplifier on and I started the timer. Notice that once we've enabled the output of the amplifier, we can see that our voltmeter is now measuring a voltage of 239 volts. However, we can still see that the current from the inverter here is still showing 0. If I update the plots and we go down here and have a look at the inverter current, this waveform here, you can see that the inverter current is very small, essentially 0. This makes sense because we haven't closed the feedback loop switch. So let's go ahead and close that switch now. Notice once we've closed the switch, the plots have updated and we can see that there's some current flow from the inverter. Now the inverter hasn't started up yet, so this current flow is still very small. Okay, now all that's left to do is to wait for the 5-minute startup timer to elapse, and then our microinverter will begin producing power. Now recall previously when I had showed you the setup for the draft case, we had created some controls for something called the external plot update. The external plot update will allow us to automatically update the plots once the inverter starts up. In order to do that, we need to first arm the plots so that once the 5-minute startup time has elapsed and the inverter starts up, the plots will automatically be triggered to update so that we can observe the waveforms during the startup process. We can arm the plots by pressing this button here. Now all we have to do is wait out the remainder of the startup time. Okay, we're nearing the end of our 5-minute startup time, so the inverter should be starting up momentarily. Once it does, you should see the plots automatically update. You'll also notice the power flow shown on these power meters change, so keep a close eye on that. Okay, here we go. It looks like the inverter is starting up. You can see the plots have automatically updated, and here we can see the output power of the inverter has increased. And we also see a corresponding decrease in the output power from the grid. So it looks like the inverter is supplying 182 watts of our 250 watt load, with the remaining 65 watts being supplied by the grid. The plots have automatically updated to show the voltage and current waveforms throughout the startup process. Here you can see the output power from the inverter ramping up. You can also see the current increasing. Correspondingly, we see the power from the grid is decreasing, as well as a decrease in the current. If we want, we can zoom in on the waveforms here and have a closer look at the current from the inverter during the startup process. Okay, let's go ahead and refresh the plots so that we can observe the steady state waveforms. If we scroll up, we can see similar measurements shown on the meters here. You can also see the measurements of the voltage as well as the current. Here we see about 0.77 amps RMS being injected by the inverter. These voltage and current measurements are in agreement with the measurements shown on the voltmeter and the ammeter, as well as the voltage and current measurements shown on the front display of the SBS amplifier. Okay, now that we've closed the loop and the inverter has started up and is injecting power into the simulated power system, let's simulate a fault in this power system and see how the inverter responds. Here you can see that I've configured the fault duration slider for a fault duration of 10 cycles. I can then initiate the fault by pushing this button here. Okay, so I faulted the system and the plots automatically updated. If we look at the voltage here, we can see that the voltage is depressed during the fault. We also notice that prior to the fault, we have normal current flow from the inverter and that the inverter is injecting power into the simulated power system. However, shortly after the fault occurs, the inverter shuts down and is no longer injecting power into the system. If we want, we could zoom in here and observe the response of the inverter during the faulted condition. Okay, so now we can see that the entirety of the load here is being supplied by the grid and that the inverter has returned to the startup procedure, meaning that it won't start producing power for another 5 minutes. Okay, now we would like to terminate our power hardware and loops simulation. So the first step is to open the loop using the feedback switch. You notice once I've opened the loop, the current from the inverter returns to 0. Next, we need to disable the output of the amplifier. Once we do that, we should see the voltage measurement displayed on the voltmeter drop to 0. Now that the output of the amplifier is disabled, we can see that the voltage displayed on the meter is essentially 0. And now we can stop the simulation. Once the simulation is stopped, we can see that the amplifier is no longer receiving any voltage commands from the simulator. Okay, that concludes today's demonstration. I hope you learned something. Thank you.